All right, so compressibility. We had talked already about compressibility as what is compressible, what is incompressible as it's related to the situation of a fluid. And then for the Mach number didn't show up on these slides here. I'll just add it real quick. Let's see. Mach number is speed of fluid divided by speed of sound in the fluid. You'll find it in your book just as well. So it's just a ratio of fluid speed to speed of sound. So why does that matter? The speed of sound, it turns out to be a pretty good surrogate or related speed to when velocity effects of fluid movement result in the fluid compressing. And this number changes according to the identity of the fluid because the speed of sound in every fluid is not the same. So it makes it nice that you just have this one number, the Mach number, and if you can evaluate that number for air or water or oil or sludge or whatever it is that might be moving quickly, then you'll get a pretty good sense of if the fluid conditions according to the flow tell you that I might should treat this flow as compressible and not incompressible. Or I know that the Mach number is pretty low, so I'm pretty safe just saying it's incompressible and treating the density as constant. The general rule of thumb as I have on here is that if the Mach number is less than 0.3 or 30% of the speed of sound, then that correlates to the density changing less than 5%, and the fluid you can just say is incompressible. You could figure out how much the density changes perhaps under some of these velocities, but what you'll find is that it's just not going to change that much. As the bulk modulus is a quantitative way to evaluate the compressibility of a fluid, not according to velocity, but according to changes in pressure. So there's lots of situations where you might be evaluating something deep under the ocean, like subsea engineering, or you might have very decreased pressure in like a high vacuum situation. So if you notice, here's the bulk modulus. Here is V over dV. This term by itself becomes unitless. Specific volume over specific volume is unitless. So the units of bulk modulus are just pressure, because all you have left here is pressure. The change in specific volume over the specific volume is really similar to the idea of a percentage change in specific volume. So that idea of how much does the volume change according to a change in pressure is based on a percentage change. It's already built in here. And that's how it's related to compressibility. One other thing to say is that you can make this dV a delta V and this dP a delta P. And you could say, well, if I wanted this change here to be 10% for a particular fluid, and this bulk modulus was constant, as it usually is, then you could figure out what change of pressure would be required to get a 3% change on this, which in this would be 1 over 0.03, because this is inverse of percent change, because the percent change is this dV over V. Moving on from bulk modulus is trying to understand ideal gas law and why does it matter for what we're doing here. This seems like a chemistry concept, but in a lot of things in fluids and thermodynamics and things related to those fields, it's actually really relevant. One important thing is to realize that you may not have seen in too many courses the pressure times the volume equals the moles of substance times a universal gas constant times the temperature. This temperature being always absolute temperature, this pressure always being absolute pressure. So there's one critical difference in the chemistry formulation versus an engineering formulation, which is that in the engineering one, we don't use moles, we have the mass of substance, which is more often how we actually see problems written as in terms of mass flow or total mass. And so this R value, you might say, well, this RU and this R, how are these different? Well, normally RU is going to be in units of something like joules per kilogram per Kelvin, or Pascal times meter cube per moles per Kelvin. So it's going to be a per mole quantity. So it's the same. That's why it's universal. It's the same for every substance. This R that's not Ru will be in something like joules per kilogram per Kelvin, whereas this one was per moles per Kelvin. So since this one is per kilogram, it really means per kilogram of whatever substance you're dealing with. So which means that if this R you look up or calculate, you just use the molecular weight to get from Ru to R. You've used a molecular weight to get from Ru to R, which means that you used a molecular weight that pertains to only one type of substance, which means that this R value only applies to that one type of substance. So if you're using this formulation for 5 kilograms of nitrogen and you look up an R value, which is in the back of your book in a table, or you can calculate it, then you can get like the volume. But if you suddenly say, well, now all of the things are the same, the mass is the same, now it's 5 kilograms of neon, and the temperature is the same, and the pressure is the same, well, the volume's not going to be the same because you're going to have to use a different R here for neon than you did for nitrogen. And that's probably, if you think about it, it'll be different because 5 kilograms of neon is not the same amount of moles as 5 kilograms of nitrogen. And that, if you go back to this chemistry, well, the moles aren't the same, so why would any of the other solutions be the same? The moles is the more fundamental idea in the ideal gas law than mass, but making it where we have a substance-specific R makes it a lot easier to use this. Now, one thing that may not be obvious from this is that you can see here there's volume and there's mass. So if I divide this whole equation by volume, then on the left side we'll just have pressure. Then we have M over V RT. M over V, should recognize that as mass density. So you can relate this to mass density directly, and that's really helpful because that means that in any problem where you have a gas and you can say that it's ideal, meaning that like as in this diagram here, in an ideal gas you don't have interactions of attraction or repulsion between molecules versus you do in a real gas, and a lot of the collisions in the ideal gas don't matter, as they're relatively elastic and they're infrequent, versus they do matter in a real gas. So if you know it's an ideal gas, it follows these two basic assumptions, then that indicates that you can use the ideal gas law, which means that if you use this form where you convert this to M over V density, then you can find the density of your fluid gas, and you now have a fluid property determined for a fluid problem from a law that really came from chemistry, and that's really valuable. Dalton's law of partial pressures, I put it here as a general review. Each gas in a mixture of gases exerts a partial pressure, and if the gases are ideal, then if you can find the mole fraction of that gas, if you had 10 total moles of gas and 2 of those moles were oxygen, 2 moles of oxygen divided by 10 moles total is 20%. And so if the total pressure of all those gases together was 100 kilopascals, 20% times 100 kilopascals is 20 kilopascals, which means the oxygen partial pressure would just be 20. You'd put 20 here, and then you could figure out based on mole fractions, or if you didn't know how many moles of a certain gas, you could figure that out based on, if you knew the partial pressure of 2 gases, but not the third one, you could say, I know the total, I know the first 2, I can figure out the third one, and then I could relate that to mole fraction. So that's really helpful in gas mixtures. The International Standard Atmosphere is a concept we probably won't use a whole lot in this class, but it's good to know because there'll be a few problems on it, and it's related to the idea of how does pressure and temperature change as you go higher in altitude. Of course, it could change lots of different ways depending on weather and climate conditions of that day, where you are on the Earth. But what this is trying to say is they used a lot of equations and assumptions to say generally this is how pressure changes and generally this is how temperature changes with altitude. So if you needed to know, oh, I'm going to fly some aircraft at 40 kilometers above the surface of the Earth, then I could figure out from a table you really can't read on this chart, but you could read a table in the back of your book and say, what is the approximate pressure going to be and what is the temperature going to be? Then you could use the ideal gas law to get the density of it, and you could also get the viscosity, which would be in that table. You would need that, or you wouldn't know how the air is going to respond to that aircraft at 40 kilometers of altitude. Viscosity itself, what we're seeing here is viscosity is resistance to shear or angular deformation. So you can look at it in terms of what you see here in these hourglasses. During the same amount of time that's elapsed, the low viscosity fluid has more because it has less resistance to flow than a high viscosity one, which is exactly what you're seeing here. Then some of this is interacting with the wall. In this picture, you can see that this one on the far right has more viscosity to it, but it's not just an interaction with the can that's in it. The streams themselves look different, and this is indicating that the way that the fluid shear between itself, even if there's not a container touching it, if it was just flowing out in the open like in space, its viscosity would still matter because it's not just a measure of resistance to flow against a solid boundary, it's resistance to flow amongst itself too. This is a diagram that illustrates how viscosity changes with temperature, and as you can see, as temperature increases, as you might expect, just like when you heat up honey in the microwave, then the liquid viscosity decreases, and that's because you're breaking up cohesive forces, which are really important in liquids. But in gases, when you increase temperature, you actually increase viscosity for some time. And that's because there's these inertial forces, which is the molecules in the gas impacting each other and creating resistance to flow. And so if you're increasing the temperature, you're moving those gas particles faster. And if they're moving faster, there's more collisions that are going to happen. So there's going to be more inertial forces of them bumping and slowing each other down. Newton's law of viscosity is really important. Basically says that there's a shear stress. Remember, shear stress is just the force per area. So the fluids sliding past each other, those parallel movements. So there's a force per area that represents resistance to flow, is the absolute or dynamic viscosity times the shear rate. And the shear rate, when you look at it in a diagram, is the change in velocity with the change in position. If you take velocity here as meters per second and divide it by just a coordinate, meters, then meters per second divided by meters is just per second, or 1/2. So a shear rate or a velocity gradient is just inverse time, which is probably not what you might expect. But if you check out inverse time and something which would be like Pascal seconds here, or centipoise for absolute viscosity, then you will end up getting something that's a force per area. This diagram illustrates how you could actually use Newton's law of viscosity to solve a problem involving shear force. So what if you wanted to know what is the force it would take to pull a plate that's filled with water here with a relatively thin distance between this stationary plate and this upper plate, and you knew that the area of this plate was 1 meter squared. Well, if you look here, this is the velocity gradient here. How is du changing with change in y position? So it's a little inverted. This is like, if it's like your standard x and y, then your velocity is like your y going this way, and then like your x, your normal horizontal axis, is your y going this way. So it's not this slope that you see here. It'd be like if you inverted it on the side. That's the slope that matters. But you can see that du dy isn't changing because it's a line. It's a constant slope. So when I say where is the shear stress the greatest in this diagram, if you go back to here, the shear stress is the dynamic viscosity times the velocity gradient. If your temperature is relatively the same throughout the fluid, then this dynamic viscosity is going to be constant. And since this is a line, a straight line, du dy is going to be constant. That means it doesn't matter where you are in this fluid here. If this is a line, then the shear stress is the same everywhere. So if you wanted to know what the force is here, you could say, well, find the slope of this line, find the dynamic viscosity of water at whatever temperature you're at, multiply those together to get a shear stress, and then shear stress is force per area. This plate we said was 1 meter squared, so if you multiply times 1 meter squared, you would get force in newtons or force in pounds force, and you would see this is how much force I have to actually pull this plate to get it moving at a constant velocity, as I mentioned up here. So the last thing is there's something in the book that discusses a no-slip condition. So what is a no-slip condition? Why is it important? No slip means that at a solid boundary that if, for example, down here, this plate is stationary, it's not moving. So the no-slip condition says that the fluid that's right next to this plate has zero velocity. So if you go all the way down here, this velocity says u equals 0. It means the plate is 0, and the velocity of the fluid actually does go to 0. This fluid at the bottom does not move. Right up at the top, at the bottom here. And then at the top, this fluid is at u, say like 1 meter per second or something. Then the fluid at the top that's in contact with it is exactly 1 meter per second. It tracks right along with the plate moving. It doesn't slip. If it slipped, it could have a velocity that's different from the solid boundary that it's in contact with. But since it doesn't, that's the no-slip condition. And we generally assume that in most fluid problems, which is how, if we knew that this was going to be a linear velocity profile, we would say, I know that this plate is going at 1 meter per second, which means that the fluid at the top is 1 meter per second. I know that this plate at the bottom is going 0 meters per second, which means the fluid here is at 0. So if you knew this distance h, you could get your constant du dy in this situation without taking any measurements at all in the fluid, and you'd know exactly what the shear stress was. And that would be important because you'd know exactly what this force would be, and you'd know how much the resistance to flow is affecting the force it takes to actually move this. Okay, I'll let you guys watch this video on your own. I think you'll be able to click it from here, but if not, I'll put a link up. And we are looking, when you look at Newton's law of viscosity here, embedded in this, Newton's law of viscosity is true for every fluid. The challenge is that is this dynamic viscosity always the same? We know it can change some with temperature, but what else could it change with? The concept of a Newtonian fluid, I think when Newton formulated this idea, he had this idea that maybe some atmospheric temperature, climate conditions will change this, but other than that, it's going to stay the same. And for a lot of fluids, it does stay the same. Here is the shear rate, the velocity gradient, and the shear stress. So tau equals mu times du dy. That means that tau versus this, the slope of this line is the dynamic viscosity of your fluid. And if it's a line, that means the slope is constant. If the dynamic viscosity is the slope and the slope is constant, then the dynamic viscosity is also constant. And this behavior where you have a line, no matter the shear stress, no matter the du dy, the dynamic viscosity is the same. These constant dynamic viscosity fluids are Newtonian fluids. They exhibit this behavior. There are also ideal fluids. If you see here, no matter the shear rate, the shear stress is always 0, which means you don't really have any resistance to flow. That's essentially the slope is 0, the dynamic viscosity is 0. So no fluid actually has no viscosity. That's why these are ideal fluids. But under certain conditions, you can treat the fluid like it has no viscosity. This is an example of another one. You can have fluids going this way up at the top or going this way out the bottom. In this particular case, as you notice here, the slope is greater here, so the viscosity is larger here than here where the slope is lower. So here the absolute viscosity is actually higher than it is here, which means that this is saying that as you shear the fluid more, as you work harder to move the fluid on this upper region, then your viscosity decreases. We call that a shear thinning fluid. It feels like the fluid is getting thinner, and in a lot of practical ways it is, in terms of its resistance to flow, with an increased shearing. You can probably observe this with different things. The opposite is a shear thickening fluid, where it might start out at a low slope and reach a higher slope at a higher shear rate. And that's what this video is about, where they actually show that a mixture of cornstarch, when you start to walk on it, and then you're having additional shear, you're making it thicker. And that's what's allowing them to walk on it in this video. So kinematic viscosity is just the absolute viscosity divided by density. That's really all that it is. There's some other things in here that are important, but one thing that you should think about is, if you know that absolute viscosity changes with temperature, and you know that fluid density changes with temperature, then if you want to know how kinematic viscosity is changing with temperature, you really have to track how both of those are changing. And kinematic viscosity is important because it just shows up in a whole lot of equations. So that tells you that it's kind of an important quantity. Surface tension is the tension that results from the combination of forces that are the fluids adhering to each other that within the molecular surface. That's intramolecular cohesion. This should be extramolecular adhesion here. So cohesion is the fluid wanting to touch itself and remain in itself, and adhesion is it wanting to go out towards a container or to like another fluid, like between air and water. So this is how surface tension as a force per length is going down with increasing pressure. This is the phenomenon, if you've seen the water striders that can walk on water because they spread out their weight enough that their weight doesn't exceed the surface tension of the water. So if there's not a whole lot of things that can do that, but if you can do that, then you can walk on water. So you could probably figure out, just for fun, if you wanted to, how big your feet would have to be to not exceed the surface tension of water, and then you could figure out how to walk on water if you can just grow your feet really big. That's kind of what surface tension is about. One way we look at it mathematically is like capillary rise in a tube. You've all seen in like graduated cylinders how you have to read the meniscus and the bottom of the meniscus to know where the height of fluid really is in something like that. You can just put a tube in water and it'll rise up in the tube if it's sufficiently narrow, because the water is attracted to the walls of the tube. It's wanting to adhere to this glass surface. So there's a balance between the forces grabbing onto the circular tube and the weight of the fluid itself, because it's having to pull up against gravity to adhere onto these walls. So those forces are balanced when it's just sitting there. This one on the left here, 2 pi r times the surface tension times the angle, this angle right here, which in water against a glass tube is just about 0, in a clean glass tube. This represents the adhesive force, or the capillary force, that's caused by this tube. So it's dependent on how thin or thick is the tube, and the angle, and the surface tension. This here is pi r squared h. That's just the volume of the water right here. So that's the volume here times the specific weight will give you the actual weight. So that's the weight of the fluid against the surface tension force. Remember, surface tension is like newtons per meter, force per length. R is a length, so that makes this all together become a force. Force equals force. Those two are equal. And what this allows you to do is you could say, well, if I know the radius of some glass tube, and I know the surface tension of water at a particular temperature, you can look it up. Then I can figure out, at a certain tube radius, how high should the water rise inside of it. You'll just be able to predict that. So it's like, well, why do I care about tubes? You might in some situations, but things like actual capillaries, like in your blood, they have capillary forces. And a good example for civil and environmental engineering is in porous media, like in groundwater. There's this region above a saturated groundwater zone called a capillary fringe. And that region exists because of these capillary forces, and these small spaces between grains actually pull water up inside. Maybe not entirely saturated, but it pulls water up here in this region, and it does matter for some areas of water flow and pollution and remediation of polluted groundwater and things of that nature. The unsaturated zone is a little different, because that just is water that remains after draining. This is saying it's actually pulling water from the main aquifer region into this other area. So if this is anywhere significant, it's going to affect some kind of groundwater balance in terms of how much water you really have available to pump or how fast groundwater is going to move. So understanding capillary forces is important. Surface tension comes in more than you might really think. Vapor pressure feels like kind of like a chemistry concept, but it is important in several areas of engineering and civil and environmental. The way to understand it, or a good way to understand it, if you put some liquid water in here, and this area initially had nothing in it, maybe some air, and it was this pressure was the same as this pressure on this side. Then, as you can see, the water is beginning to vaporize here to fill this space above the liquid. It's pushing this down, which means that it's increasing pressure up here relative to what's up here. So the pressure is pushing against this external area here, and there is basically a positive pressure that comes off of any liquid. There's an amount of vapor that wants to exist above any liquid in a condensed state that is in equilibrium with it. So there's some vapor up here at a constant pressure, there's some liquid here at a constant mass, constant volume, and these two are constantly condensing and vaporizing, but it's an equilibrium. It's a dynamic equilibrium. So like for example, if you open a can of gasoline, you'll smell vapor right away because there's a vapor pressure of gas that's relatively high that has been established inside that gas can, and it's wanting to escape so that you can smell it. Every liquid has this property. The vapor pressure tells you a lot about how volatile the liquid is. Okay, so why does it matter? You can look at different ones here to get a sense of how volatile things are. If it wasn't obvious to you, something like carbon dioxide, it vaporizes pretty rapidly and sends off a lot of stuff. So it's more volatile than water by a large factor here on vapor pressure. Ethanol, if you have some rubbing alcohol or just some ethanol from a drink that's an alcoholic drink, you can smell that much better if you dump it on a table than you can water because it has double the vapor pressure of water. So here's a phase diagram of pressure versus temperature and gas, liquid, and solid. A lot of substances follow a diagram like this. There is a pressure here. This pressure between liquid and gas is the vapor pressure. So how this works practically is, let's say that this is 740 millimeters of mercury, and the temperature outside is right here, basically the vapor pressure is going to correspond. I'll say how to say this. All right. So I guess let's take another. Let's say that the temperature outside is like 80 degrees Celsius. And so if it was 80 degrees in whatever container you were in, the vapor pressure would be like say 740 millimeters of mercury. What this is saying is that if the pressure in that container, or the atmospheric pressure, if it were to get lower and lower and lower from like 800 millimeters of mercury down to 740, that pressure is pushing against that liquid. And so eventually the external pressure of the atmosphere going down from 800 to 740 is eventually going to equal the same as the vapor pressure. And when that happens, when the external pressure in the environment or a system is the same as the vapor pressure of that liquid, that's what boiling is. A liquid will begin to boil. So and you can see those pressure and temperature things are related. In the normal world, we'd say, well, the pressure outside is 760. That's 1 atmosphere, and that corresponds to a temperature of 100 degrees Celsius. So when the temperature of the water can increase to that, then it raises the vapor pressure of the water from it's going up, it's going up, it's going up, and so eventually the vapor pressure of the water is the same as the atmospheric pressure, and that's why boiling happens at 100 degrees C. Probably is a little confusing from what I said there, but I think the take home from this is that the vapor pressure of a liquid determines when it boils, and if you can make the external pressure in the atmosphere in your system the same as what the vapor pressure is, that's when boiling is going to happen. So related to that is this idea of cavitation. Some of y'all may have heard of it. We'll talk more about it later. But cavitation is when you have some fluid that is flowing at a particular vapor pressure for its temperature, and a lot of times that pressure is really low. But you need to know what that is, because if you create a condition in flow where the pressure in the flow is less than the vapor pressure, then that liquid is going to boil, and it's going to suddenly form these bubbles. And that's, you can see some bubbles and gas along this cavitating boat propeller, because you create low pressure zones whenever you have a rotation like that in flow from these veins here. That's bad. That's bad because you'll bring fluid through a zone of low pressure, and it'll vaporize into bubbles. And then as soon as those bubbles go into a higher pressure, it's higher than the pressure inside the bubble, and the bubble rapidly collapses and creates a shock wave. And that shock wave does a lot of damage to equipment like propellers and pumps and pipes and elbows and things like that, in a lot of flow systems. Very damaging. So you want to know when you're designing something like a propeller, a pump, anything that's going to have changes in pressure, what is the vapor pressure of this fluid that I'm pumping, moving, spinning, and am I creating ever a condition where the pressure inside is going to, even for a minute or even for a small area, have a pressure lower than the vapor pressure? Because if that's happening, then you need to adjust your design so that you don't create these bubble shock waves. All right, so that's pretty much covers this whole topic area. I've just kind of gone over a couple other topics. You want to know the distinction between these terms: solid, fluid, liquid, vapor, gas. You need to feel very comfortable converting between fluid mass, weight, and volume properties. You should memorize those different equations for specific weight, specific volume, specific gravity, and density. You should be able to just recall all four. Just, what are the four? Just recall them from memory. Understand what bulk modulus is, how that's related to fluid compressibility as change with pressure. Understand the ideal gas law and Dalton law, especially how the ideal gas law will help you find density in specific volumes of gases. Be able to read and interpret values off of the standard atmospheric values and think about applications in higher altitude where those will matter. You need to understand how to calculate dynamic viscosity from kinematic viscosity and calculate kinematic viscosity from dynamic viscosity and know the different units. Be able to just look at something and say, aha, that thing is 0.005 centimeters squared per second. It must be a kinematic viscosity because they only have units of length squared per second, or length squared per time. Recall Newton's law of viscosity from memory and understand how absolute viscosity and velocity gradient actually create shear stress, and understand what makes a fluid Newtonian and non-Newtonian according to absolute viscosity and how it behaves when it's being sheared according to Newton's law of viscosity. You need to be able to solve these problems of capillary rise and understand exactly what surface tension is, at least so you can explain it a little bit, and know how liquid vapor pressure, like what it is, how to compare it, and how it relates to boiling and cavitation. There may be some other applications later, but those two are both really important for civil and environmental engineering applications. So that's the rest of that chapter. Please follow up with questions if you have them.